Hello, everyone. Thank you so much for joining us today. This is the first edition of Marine Renewables Canada's Ask an Expert webinar series. So we're very excited that you're joining us on this first edition of the series. In order to get this webinar series started in a good way, I just want to take a moment with everybody on the call today to recognize and acknowledge the traditional territories and Indigenous peoples of all the lands that we're on today. We're meeting virtually. So in particular, given that we're coming together today to discuss offshore wind, I just wanted to invite us to think deeply about renewable energy in particular, and to reaffirm our commitment together to improving relationship between nations and improving our own understanding of local Indigenous peoples and their cultures, so that marine renewable energy projects in Canada can move forward inclusively and respectfully. So as I mentioned, this is the first in a series of webinars that Marine Renewables Canada, or MRC, will be hosting. For those of you that aren't familiar with MRC, we are the National Association for Tidal, Offshore Wind, Wave, and River Current Energy. And over the next year or so, we're going to be hosting a series of webinars about offshore wind with experts to tackle Canadians' biggest questions about offshore wind. So before turning it over to our guest expert, Mark, today, just a few housekeeping notes. So we are recording. As I mentioned, we're going to be posting this on MRC's website and YouTube page. The bulk of the webinar will be Mark's presentation today, and we'll follow that up with a question period. So I invite you to use the chat function, which we'll be monitoring throughout the presentation, but Mark will be taking the questions at the end, so we'll have a separate question period at the end. So please feel free to use the chat function for those questions. We'll be able to keep a record of your questions that way too. So if we don't get to one of your questions today, we're going to do our best to follow up with you afterwards. The intention of this webinar series is really to respond directly to your questions, Canadians' questions about offshore wind. So we encourage you to ask them now while we have our expert with us. All the webinar topics in this series have been informed by a survey that we conducted. So we asked Canadians really, what are you curious about in terms of offshore wind? And the aim is to help fill the gaps in all of our knowledge as we start to contemplate deploying offshore wind in Canada. So now is the time to ask your questions. Please feel free to do so. And without further ado, I'd like to welcome Mark Severy, a research engineer with the Pacific Northwest National Laboratory in the United States. Mark works directly in offshore wind energy, focusing on the collection and analysis of data to assess environmental risks of offshore wind, transmission planning, and much, much more. He's going to get our webinar series started off today with an overview of offshore wind technologies to give us a broad sense of what it takes from a technology and infrastructure perspective to build an offshore wind sector. So thank you so much for being here with us, Mark, and for getting this series started, and I'll hand it over to you.
Thank you. And I just started a screen share. I just want to confirm you're able to see the right screen.
Looks great to me. Thank you.
Yeah, no problem. So I'm happy to be here today and talk about offshore wind. All my work, or at least the majority of my work now, is around offshore wind technology, specifically in the United States, but also in some aspects trying to learn from the experience in Europe and abroad to bring that knowledge to our country's development process. So the Pacific Northwest National Lab, where I work, I'm an engineer / scientist there, and I work on a variety of projects like that were mentioned. Our lab is U.S. Department of Energy laboratory, so most of the work we do is publicly funded and publicly available to find any information. I won't be talking specifically about the work I lead, but I'm going to be broadly talking about offshore wind technology and the industry. So let's just start with the basics. What is offshore wind energy? You may already know this, but offshore wind energy is essentially wind turbines that harness energy from the wind to produce electricity. The reason it's called offshore is because the turbines are placed on structures either in the ocean or in a lake, but somewhere over water. And then cables are used to transmit that electricity back to shore and connect to our electricity transmission and distribution system. So there's several main components of an offshore wind farm. You have starting with number one, the turbine and the foundation. Number two is the inner array cables. These are cables that connect between individual wind turbines and string them together and bring them to number three, which is a collector station that gathers power generated from multiple wind turbines. And then number four is the export cable, which is a cable that brings that power back to shore. At some point, that cable is typically buried, and then at some point it pops out from underneath the seabed and comes to shore. This may be through a beach, through a rocky habitat. And then finally, number six connects to an onshore substation, which allows power to be distributed to homes, businesses, industrial applications, etc. So that's not all that is involved with offshore wind development. Those are just the components that would be used for normal operations and maintenance, or normal operations and production of electricity. But how is offshore wind built and maintained? You need several other components to do this. You need a supply chain to provide the equipment, the tools, and all the components. You need ports to assemble and service the wind turbines and associated facilities. And then you also need a whole fleet of vessels, either dedicated to this or across multiple shared uses that can build, maintain, and service the wind farm. Secondly, we want to think about how does offshore wind interact with society, the economy, and our environment. So through this, you might consider what types of jobs are created by developing a new industry. How does offshore wind interact with other ocean users, such as fishing industry? And how does offshore wind interact with, either positively or potentially negatively, with existing wildlife and the ecosystem in the area? So all that coming together, this is just the intro. There's many pieces associated with offshore wind that are required to build this industry. So today, what I'd like to cover is first starting with the basics of why is there an interest in offshore wind energy, and then getting into a little bit more detailed description of the different components of an offshore wind power plant. Third, talk about the infrastructure needed to support offshore wind, and then talk about the process that is in place, at least in the United States, so I can bring that context for how offshore wind is permitted and developed. And then lastly, just pretty briefly discuss how offshore wind can interact with other aspects of our society. And then, of course, I'm really excited to open it up to a discussion with you all. So basics of offshore wind energy, and this is really getting into why is there interest in offshore wind energy. This here shows a map of average wind speeds 100 meters above the surface across all of Canada. Darker colors are higher annual average wind speeds. If you look for the darkest blue, you see that's really offshore the eastern coast of Canada. And so high wind speeds are important because they can produce more power. So when people are thinking of installing or developing wind power, you look for, in general, areas with high average wind speeds. There's a few other characteristics, of course, that are important from an energy perspective, but this is one of the core pieces. Higher wind speeds produce more power. This curve in green shows the wind speed on the horizontal axis and then the power output on the vertical axis. So at low wind speeds from 0 to 3 meters per second, for example, a turbine won't be generating any power. And then as the wind speed increases, the power can increase until it reaches this kind of flat portion on the curve where a turbine is producing its rated power output. In this case, this is a 15 megawatt turbine. So this is a really large turbine that would be installed offshore. And this gray area that I highlight on the curve is that annual average wind speed that we saw on the eastern seaboard of Canada previously. And this helps show why that annual average wind speed indicates that there's a really strong interest maybe in offshore wind development. Annual average wind speeds in the 6 meter per second to 7 meter per second are kind of on this upswing portion of the curve, so that the turbines over the course of the year wouldn't be producing their full rated power. So that's number two. Well, it's really number one. Strong wind speeds are important for wind development. The second point I want to make about why there's interest in offshore wind energy is that offshore wind complements a suite of other renewable energy technologies. And as Canada is shifting towards carbon-free or clean renewable sources of electricity, it's important to balance the generation profile from different sources. So this plot shows a green curve of solar, just for a typical day. This is data from California, where it's sunny towards the middle of the day, and you can produce power at that time. When overnight, there's no sun, so you cannot produce power actively at that time. The blue curve shows land-based wind in California, and you see its generation profile kind of dips down in the middle of the day and peaks up towards the evening. Offshore wind, on the other hand, is fairly consistent throughout the day. And combining these three resources together provides opportunity to balance and manage an electricity generation and transmission system to deliver power when it's needed, where it's needed. If there's periods where there's no wind and no sun, it's hard to deliver the power you need without a large storage asset. So it's important to capture the different kind of weather patterns and meteorological phenomenon across a wide geographic area to say, okay, the wind's blowing over here, and we can capture energy even if the sun isn't blowing, even if the sun isn't shining somewhere else. So that's point number two. Number three is offshore wind is a really large scale power generation facility. So historically, power plants were generated or were developed in really large, with large power outputs. Think of historic nuclear generators, multiple gigawatts in scale. Think of large coal generating facilities or natural gas facilities. These are large devices. And as we've shifted towards renewables, oftentimes these are smaller, more distributed network of generation assets. Offshore wind, because the resource is so strong, the wind speeds are so high, you could have really large power plants and really large turbines that produce a lot of power. That helps fill in the gaps as we transition away from and decommission some of the older, larger fossil fuel powered plants. So for example, I have one statistic that I did a little bit of calculation on is a single 17 megawatt wind turbine, which is this larger future turbine shown here, is equivalent to a 25 hectare solar farm or about 2,000 houses with rooftop solar. So that's just one single turbine can displace or is an alternative to a really large field of solar generation. So it's really not, when I think about renewables, I don't try to think of this is this technology versus this technology. It's really all of them together to get the type of generation profile we're looking for. Fourth, why is there interest in offshore wind energy is often loads, electrical loads are concentrated along the coastline. So we see this in the US, both on the West Coast and the Atlantic coast. The highest density of power users are on the coasts, which is where offshore wind energy is, versus some of the best land-based wind resources are really towards the center of our country. And it's harder to distribute that power towards the load centers where they're needed on a large scale. And then lastly, workforce and economic development. As I pointed out in the introduction, there's a whole supporting industry that goes along with offshore wind, and there's opportunities to capitalize for workforce development, for regional economic development, as this industry could potentially grow. So that's kind of the starting point. And now I'll transition to discuss what are the basics of the technology? So for the first thing we think about is the turbine itself. These are similar to land-based wind turbines that you may have seen or that you may be familiar with. The difference being offshore wind turbines are larger, they're taller, and they produce more power. Part of the reason we want to do this is because it's expensive to develop offshore wind. There's many more challenges than there are to develop a land-based wind farm. And so each turbine that you install, you want to be able to extract as much power as you can from it. Wind speeds increase the higher you are above the surface. So you might see 5 meters per second at the surface. That could be 10 meters per second, 100, 200 meters above the surface. So building taller wind turbines with larger blades and a wider rotor allows capturing or harnessing more of the wind power. So offshore wind farms have kind of grown in turbine size from the initial wind turbines that were installed in the US off Rhode Island are 6 megawatt wind turbines. And now turbine manufacturers are producing 12 megawatt turbines, 15 megawatt turbines, and there's projections out towards 2035 where the turbines will be rated for 17 megawatts of power. What this means is the turbines are tall. They're about the center of the hub. I just put some example numbers here, would be about 150 meters above the surface. The blades are about 120 meters. And at the top, that comes to about 275 meters high. And there's roughly 25 meters below that bottom sweeping of the blade. In general terms, there's two types of offshore wind. There's fixed bottom offshore wind, shown here on the left, where the turbine's attached to a foundation, which is firmly attached to the ocean floor. This works in waters that are relatively shallow. So a typical cutoff we think about is maybe 60 meters of water depth. Those are suitable areas to do fixed bottom offshore wind. But as water gets deeper, you cannot install something that deep directly into the seabed. So instead, there would be floating offshore wind. In this case, shown here on the right, is the turbine attached to a floating substructure, which is then fixed in place through a set of mooring lines or cables that are attached to anchors that dig in or affix themselves to the seabed. Floating wind has been proposed in waters up to about 1,000 meters deep and maybe a little bit deeper on the west coast of the US. And the technology is kind of in development, has been demonstrated through several pilot projects in Europe, and they've seen good success with that. To build a whole offshore wind plant, we're not just thinking about a single turbine, but we're thinking about a set of turbines. This could be a dozen, it could be 20, it could be 50 turbines, depending on the size of the area that's identified. Turbines are generally located relatively far from shore, 20 to 60 kilometers from shore, and then they're spaced out fairly in a pretty broad pattern so that they're not really interfering with one another. A general rule of thumb that's used in high-level planning is that you take the rotor diameter of a wind turbine, which I showed 2 pictures ago, we showed about 250 meters. Then you multiply that set by 7 and space them about that far apart. So that's roughly 1.5 to 2 kilometers apart per turbine. This changes based on the local wind patterns. So if there's really predominant wind speeds in one direction, you may space them out further along that. And the reason you want to spread them out quite a ways is to avoid wake effects. So this illustration shows how just downstream of a turbine, the wind speed changes slightly. I mean, you're pulling energy out of the wind, so you don't want to place another turbine directly behind it, or else the wind speeds will be slightly lower. So that's why you want to space them out to give time for those turbulent flow dynamics to really dissipate and it to be just a general wind speed pattern. So that describes most of the basics for the turbine and structures. And next, we'll look at some of the electrical cables. And I showed this pretty early on, but within the wind farm, there are inter-array cables that tie different strings of turbines together and then are collected at an offshore substation or collector station before coming back to shore. This graphic shows a wind farm from the top. But here on the bottom, we can see what that would look like from the side, both for fixed bottom offshore wind on the left and floating on the right. So if we look at the fixed bottom, you can see how the inner array cables come out of the turbine foundation and are buried, and again connect to another turbine and are buried, and then again would be buried going back to the shoreline. Sometimes there's portions of the seabed that are rocky or particularly hard that you cannot cut a trench in them. And in those cases, the cable may come out of the seabed and be placed on the shore with some protection over it. That could be some rocks placed around and on top of the cable, or a concrete mattress laid on top of the cable to protect it. For floating offshore wind, shown on the right, there's a slightly different setup for the inner array cables and the export cable, where generally the inner array cables would be floating in the water with little floats on them to attach multiple turbines together. And then that cable would be draped all the way down to the seabed before going the long distance back to shore. Similarly, the cable on the seabed would ideally be buried if the local conditions allow for that. Once that power arrives back on shore, I'm just going to play a little video that our lab has, hopefully just goes in the background. Once the power arrives back to shore, it needs to be connected to the grid. Oftentimes, the grid may need to be built up to accommodate the amount of power that's connecting at that substation onshore. So for these two wind farms, you see a case where they're coming to this little substation here or the substation here, and those may need to be built new or reinforced if there's an existing point of interconnection there. So for transmission interconnection design, I pulled up a map of Nova Scotia's transmission system, and all the different colors of this transmission system indicate different voltage levels of transmission. Higher voltages can transmit more power with less loss. So in this case, the green show the highest voltage transmission lines. These are generally the tallest structures on the largest metal transmission towers, and they can transmit power over a long distance with fairly low losses. So interconnecting offshore wind would require a substation and pretty likely the highest voltage transmission system available. This is very similar to developing land-based wind. So I just zoomed in here to show how there's a land-based wind farm in the center, and you just see a small transmission line going from the wind plant back to one of the backbone cables. So not only do we need to think about the offshore component, we also need to think about how the electrical components connect back to the shore. And then once on land, are there reinforcements that are needed to support the power distribution to homes and businesses around the area? So this, again, just highlights that power coming back to the onshore substation and then through the transmission tower to businesses and homes. There's multiple ways to connect between the wind plant and the onshore substation. And this is a question that comes up with transmission planning, particularly when you're thinking about multiple wind farms connecting to multiple different areas. There's what's called a radial interconnection topology, where each turbine here represents a whole wind farm, not just one single turbine. But in a radial connection scenario, each turbine is connected back to a single point of an interconnection on land. This allows that power to just be distributed to one location. An alternative to that is developing a networked transmission topology or a meshed grid. This allows multiple wind farms to be connected to one another offshore, so that power can, from turbine or wind plant A down at the bottom, be transmitted back to shore at this point here, or at other points further north or south along the transmission backbone, as we would call it. So there's just multiple ways to interconnect multiple wind plants, and it just depends on what are the needs of the transmission system and how does load vary, electrical load vary across different locations. Next, I'm going to discuss some of the supporting infrastructure for offshore wind. So the first thing that I'll discuss is port infrastructure. So ports are needed for multiple phases of installation and operation. You need ports for fabrication of devices, staging devices, assembling devices, storing parts or components for the wind farm, and then also to service the wind farm. The requirements for port facilities, it can be a single port, it could be a combination of multiple ports, but what you need to have is an on-land area for the manufacturing or staging, a dock, a berth, or something along the coastline or shoreline of that port to allow the components to go onto a vessel or into the water. And then a navigation channel, which in this example is just this darker blue in the water, that is a deeper area of that port where large vessels or floating turbines can move offshore. So this is just a concept for a new port facility that's being planned in California that shows how some of those components or aspects of the port are being developed. You'll see that there's areas for manufacturing. This may be buildings and facilities. There's a large flat concrete area for laying down different components. So they show some towers and blades on the port here. There's an area for assembling. These triangles are different floating substructures in the concept. So those would be assembled here and then brought to the quayside or the dock in order to stage them and then load them into the water. And this area is, a couple acres of land. And then there's also an operations and maintenance dock that they show here that's much smaller. Like the requirements there are really just having some vessels to be able to transport crews and equipments offshore. So to do an installation, the methods vary based on a fixed bottom turbine or a floating turbine. With fixed bottom, all of the parts are transported to the site. And then the first thing to do is install the foundation. This example shows it's called a monopile foundation. It's just one large tube or pipe that is hammered into the seabed. And then around that at the bottom, there's like a gravel or concrete mattress or another device that's placed around it to prevent seabed from eroding next to the turbine. So the installation of the foundation happens first, and then on top of the foundation is placed they call it a transition piece that allows the turbine to be attached between the foundation and then the turbine tower. So all of that is done at sea. To do it, you need a few specialty vessels, one of them being a jackup vessel, which helps provide a stable platform. And then you also need a heavy lift vessel and equipment in order to hammer the monopile into place, or there's many other types of foundations that don't require the same installation methods, but still do require some specialty vessels. For floating offshore wind, the assembly, the installation method is slightly different. In this case, as I showed at that port example, the whole turbine and foundation and substructure is assembled at the port, placed in the water, and then towed out to the site. So here you see a tugboat and a few vessels next to it, towing a floating wind turbine out to the ship, to its location. Once it reaches that location, the mooring lines would be installed with the anchors, and the electrical connections would be made at sea. Once the turbines are up and running, again, there's multiple options to maintain and service them. If there's preventative maintenance or minor repairs that are needed, those can often be done at sea, whether it's fixed or floating. You just bring a vessel out there with crew and the appropriate equipment, and you can generally service small things or maintain it for optimal function. Major repairs may require the turbines or individual components to be brought back to shore or a port facility. For floating turbines, you could feasibly tow the whole substructure back to shore, or for fixed bottom, you can't bring the whole structure back to shore, but you could potentially take a component back to shore for maintenance. And then the last phase of offshore wind installation and operation is really the decommissioning phase. So we don't want to forget about that. So all planning for large wind parks is generally, they think about a 25 to 30-year lifetime to operate and produce electricity. And then after that, you have to figure out how you're going to remove this device. And in the US, the regulations require removing anything installed in the seabed down to 15 feet below the seabed, unless there's authorization for what they call partial decommissioning, in which case you can leave some of the structure attached to the seabed. The reason that partial decommissioning is often done is because that structure becomes part of the environment offshore, and it becomes a new habitat that many creatures will attach to and live by and thrive off of the animals connected to it or living nearby. So we've seen this a little bit in oil and gas, where offshore platforms have been left at site, and they call these rigs to reef or artificial reefs, where the structure is left in place because it's actually providing a benefit to the local environmental communities. So to do all this work, there's a variety of vessels that are needed. I just show some pictures of some example vessels here. I don't need to go through all of them in detail, but it just kind of highlights the breadth and amount of specialty vessels that are needed, from a cable laying vessel for installing the cable to a jackup barge for installing a fixed bottom offshore wind turbine, to smaller vessels that are needed to transfer crew for servicing the equipment later down the road. And then the last piece I will touch on in this section is the supply chain. So far for the supporting infrastructure, we've talked about the ports, we've talked about installation and maintenance and decommissioning, but there's also the whole surrounding industry of how do you build the electrical cables, how do you build the turbine blades, the electrical components that go inside the turbine. And so to do that, there's a whole supply chain associated with the supply of those parts. This chart just shows an assessment that was recently completed in the US of how many new manufacturing facilities would be required to meet our nation's goal of 30 gigawatts of offshore wind by 2030. And we found 24, or I think, yeah, it looks like 24 new manufacturing facilities are required, and for these different components. If it's too small to read, most of them over here are foundations and turbine components. And then some of the pieces over here are more electrical components, floating platforms, or mooring components as well. These facilities for the supply chain don't need to be located directly next to or adjacent to where the wind farm is installed. And this is kind of highlighted just with this map from the same study that shows how some of those jobs for the supply chain would be distributed across the country. Certainly, we do see a concentration near the coastlines where offshore wind is of most interest, but there's also jobs and industry that's created across the country to support this. So that's the end of that section. I'm briefly going to cover the development process and then a few other considerations, then we'll open up for questions. So the development process, I just have the US context here, and it's managed by an agency within our government called the Bureau of Ocean Energy Management. They lease the area offshore to developers and then do the permitting for the facilities that are proposed. So there's a whole process starting here on the left where an area is identified and it goes out for public comment and identifying interest and concerns about that area. That area can then get refined to smaller and smaller areas and then eventually pulled into a leasing notice, which says there's this area that is up for lease to a developer. The Bureau of Ocean Energy Management holds an auction for that. And then that indicates who has the rights to develop there. Once they have the rights, that doesn't mean they have a permit and approval to build a plant, but that gives them time to plan their site assessment and allows them to operate equipment offshore there, and then develop what they call a construction and operations plan that they provide to BOEM, and then BOEM permits that through our National Environmental Policy Act to see if it's suitable or if there's mitigation measures that they need to apply. Overall, the process takes quite a bit of time. I'd say on the fastest end, it could be maybe 7 years, but more likely 10 years, I think, from identifying an area to actually having steel in the water. So in the US, there's interest for offshore wind development on all coasts, the Atlantic coast, West Coast, the Gulf of Mexico, Hawaii, and even in the Great Lakes. This shows just a few different areas offshore the North Atlantic, where there's several areas down here that have been already leased to developers. Then there's a larger area that is right now really in the early phases where it's called a call area, where it's a large area that's just open for public comment. So the status of offshore wind in the US, right now, there's 42 megawatts of offshore wind installed. This is, I believe, just 8 turbines. So that's way down here. You can barely see it on the chart. But if you look at everything that's either under construction, approved, in permitting, or developers have just recently won a auction to lease that area, the total pipeline is almost 10 times the amount of what's currently in operation. All that to say, there's a lot of work being done. There's a lot of questions in the industry and a lot of research that my lab and other labs are doing to help understand the impacts. So that brings us to what other considerations are there for offshore wind. I'm really just covering the technology piece here, but there's a lot more that goes into it that we are researching in, and a lot of my work is involved with that as well. So importantly, we need to consider these things. How does offshore wind interact with the local environment? And I just put this link here. It's from a report that I helped develop about the different environmental effects that we've seen from offshore wind. Not only do we need to consider the environment, we also need to think about human interaction. So how does offshore wind affect the regional economy? How does it change tourism, jobs? Does it bring new educational programs to the area? Things like that. We also want to think about how does new infrastructure on the ocean interact with existing uses of that space, whether that's the fishing industry, for telecommunications cables, or other industries that are placed offshore. And lastly, but certainly not least, is understanding how offshore wind connects with the local culture. If there's heritage or traditional rights or interest in areas offshore, and does development of wind interfere with that? Does it support that? How is it seen as part of the community, or is it seen as something outside the community? So making sure communities are on board and supportive, I think, is an important aspect to having successful projects. So all that to say, it's not just the technology, but it's really the environment and society, and bringing them all together to understand how and if this technology does really make sense. So with that, that was my last slide, and I just popped up my email address. You're welcome to email me for follow-up. I do see that a couple questions came in, but I wasn't able to read them. But I'm happy to open up for that discussion.
Thank you so much, Mark. That was a really great overview, and a lot of our follow-up webinars are going to touch on, especially some of the things you brought up in your last slide. So that was perfect. Thank you very much. Yeah, we'll open up for questions. If you do use the raise hand function, I should be able to unmute you if you'd like to ask your questions live. But we can start with the two that are in the Q&A. Mark, if you're able to see them, why don't you go ahead and start with those? And then if anyone else has questions, feel free to raise your hand or type it in the chat.
Great. Yeah. So I see the first question saying that wind is a resource that doesn't run out. So are there examples of when offshore wind plants have been recommissioned rather than decommissioned? And I think what has happened, at least offshore, none of the plants are old enough. There's a few in Europe that are running on like maybe 15 years of operation, so that they're really just now starting to think about recommissioning or decommissioning. What I would reflect on is what's happened in the land-based wind industry, when a lot of sites that were developed in the early 2000s or late 90s are now kind of at that phase where they would maybe be at the end of their service life. Technologies have changed with the turbines so much that recommissioning is a really good option, because you can upgrade from what may have been a smaller 500 megawatt or 500 kilowatt turbine to maybe a 2 megawatt turbine, 4 times the size at the same site. So I think the question about recommissioning versus decommissioning really follows the pathway of technology development. At certain points, it does make sense to upgrade the equipment rather than pulling it off altogether. Okay, and then the next question, it says, how has the US wind industry approached energy storage for energy from offshore wind, or is everything sent back to the grid? This is an emerging question that there's quite a bit of research on. Using energy storage is one important way to help alleviate some of the differences about when renewable energy is generated. So there was an initial chart I showed that showed solar during the middle of the day, but not at night, and batteries can kind of extend that operating period. Offshore wind has been thought about in the context of energy storage. We've thought about batteries and done a little bit of modeling where we show a small battery system can help overcome small deviations in wind energy output, but it doesn't help when we're thinking about long duration changes in the wind pattern, just from season to season or week to week. And from there, what's being studied is more like wind to hydrogen. Are there ways to develop other products that can be used, such as hydrogen, for storage and then generation at another time? I'd say that a lot of that work is is being done now, to think about what's going to happen 10 years from now or 15 years from now when there's more renewables on the grid and less fossil fuel capacity to just fill in gaps by turning on a power plant when you need it. So we don't have the answers there, but I think it's really like consider all and many options to see how you can operate a grid in the future. Next question. I see a lot of them coming in, so thank you. I'll try to get through as quick as I can. The development of offshore wind farms in Nova Scotia waters will likely impact commercial and indigenous fishers. How can competing interests between offshore wind development and commercial fishers be best managed and drawing from the experience in the US? This has been challenging. This is definitely challenging in the US, both for the fishing industry and for the offshore wind industry. So far, I'm not saying, I don't know if this has been a good solution, but there's been community benefits packages that have been put in place, but for developers to essentially compensate for lost fishing grounds. I don't know if that serves all the needs of the fishing industry or for indigenous fishers. So in many ways, new structures should be built through talking with those folks that could and may be affected early on and seeing how wind could impact them or possibly benefit them. I'd mention a few other things is that in the US, there's restrictions around having fishing boats go through a wind farm. That's not true in all areas. In the UK, fishing boats can go through wind farms, and I think that the relationship there has been slightly better. And I don't know what the rules are in Canada, so I can't directly speak to it. But I would say that communication early and often is important because offshore wind doesn't necessarily need to be a bad thing or an exclusion for the fishing industry. We've seen, and we have seen from an environmental perspective, these structures, tons of mussels go on to these structures. And then because of that, tons of fish come around the structures, not only in the midwater zone, but also at the benthic zone, because there's a lot of organic deposits that happen kind of around the base of the structure. So it doesn't necessarily need to be a bad thing, and it's just worthwhile having those conversations early. All right.
I think there was a question just before that, Mark, from John Bruce. Are you seeing that one?
I see it now.
Great.
How are areas selected for the initial step in the lease process? Who does the analysis to determine if it would be of interest to developers? Is that BOEM? I'd say generally it is BOEM that makes that determination. In the US, they often rely on some of the national labs like our lab or National Renewable Energy Lab to do an assessment of wind resources. What's been done more recently is, I think in the beginning, it started with what are the technology limitations? What depth can you install this equipment? What type of seabed do you need? And what is the wind speed? Now, BOEM has been taking a slightly broader kind of marine spatial planning approach that considers not just the technology and the wind speed, but then also environmental factors. Are there whales that frequent this area? Are there sensitive species in this area? What are the other ocean co-uses in this area, like the fishing industry, and trying to plan for areas that minimize impact to other ocean users in the environment. So it's been BOEM that's been making that early determination now, but you start with that one larger area and then it can get refined or become smaller, or even we've seen it shift sometimes on the West Coast. Okay, next question from Kevin McLean. For floating offshore wind, what transmission or connection method will be prevalent? What voltage levels will they be running at? Thanks. Floating offshore wind will be large farms. In the US, these will likely be a gigawatts scale or so. These would connect at 500 kilovolts if you're using AC or alternating current, or 525 kilovolts if you're using high voltage DC or direct current technology. Essentially, the highest voltage we can do And then what are the methods? I had mentioned those like radial interconnections, which is the individual lines, or a backbone connection that would allow kind of interregional flow of offshore wind generation. Right now, because we're in the early phases, all the initial farms are being planned for radial point-to-point interconnection. We're doing work at our lab, and there's also work at other labs to kind of investigate how backbones can provide more benefits. And what we've seen is, yes, if you're looking out to 2045, 2050, a backbone does provide more benefits. For example, on the West Coast, the backbone, not only if you connect between Washington and California and have 3 or 4 offshore wind farms in the middle, not only can you deliver power where it's needed, power is needed in the Pacific Northwest in the winter, and then power is needed in California in the summer. It makes a pathway for offshore wind, but it also creates a pathway for land-based resources to move between regions. So I think there's a lot of benefits to that if it's really like a large-scale system you're looking at. Okay, 2 questions. One, is it true that the shortage of required marine vessels or port infrastructure will impact desired offshore wind targets, i.e. the 30 by 30 target in the US? I think that I wouldn't say it's going to, I would say it's something that the industry and the government's working on addressing. We don't have all the vessels. There's a lot of restrictions about what vessels can be used, and we're doing the work now to hopefully address that 5 years from now. But it's definitely a challenge. Number 2, what is the typical offshore wind farm in megawatts, and what is the typical cost per megawatt? I'm not going to, typical size, probably 400 megawatts to 600 megawatts. Certainly it depends on the size of the area. I think a rule of thumb, we say 3 megawatts per square kilometer. But if you follow up, I can provide some resources and confirm that number. And then in terms of a typical cost, I don't have the number in the top of my head, but if you search for National Renewable Energy Laboratory annual technology baseline, they update every year what are the costs today and projected costs of different technologies, including offshore wind. Okay, Ian McPherson, 4 questions. I hope I can get through these. 1, how far offshore would a typical substation be located? It generally would be, if it's an offshore kind of collector station or substation, this would be like within the bounds of the wind farm. So if the wind farm's 30 kilometers from shore, substation is going to be 30 kilometers from shore. Are the substations fixed and floating? We have the same challenges with, or it's the same decision point. What if it's a fixed bottom offshore wind farm, is it be a fixed bottom collector station? If it's floating, substation will be floating. Floating substations, like very early phase in technology development. So there's a lot of work being done both by industry and I think also some support from the government to help improve that technology. It's not that it can't be done, it's just that it hasn't been done because there hasn't really been a large need for it. 3, hearing costs have escalated quite significantly in the past few years. Does this line up with your findings? Yes, I mean, I think this is just, it's been 1, supply chain, 2, inflation that have made costs go up instead of costs going down, which is what has been projected. The supply chain issues from COVID and inflation, like I think the economists didn't predict that happening, at least the energy economists looking at offshore wind, we project costs going down because as more people build these things, we get more experience, we get more facilities to help bring the cost down. So I think, again, it'd be useful to check out that NREL annual technology baseline to see where those costs line up. Number 4, yeah, is the primary cause of this escalation? I think the primary cause is probably inflation. Escalation costs should actually be going down as we learn more about how to deploy this technology. I want to do a time check. We have 30 seconds. Can I keep rambling or
if you're happy to keep rambling, Mark, please go ahead. But we want to be respectful of your time as well, so we can always get back to folks with written answers.
No, I'll get through all of them, and then if there's more that we don't have time for, just send an email. I'm happy to chat.
Thank you.
Yeah. So a question from Mark: many jurisdictions are implementing marine protected areas, marine conservation areas. Is it expected that these areas would be incompatible for offshore wind farms? It really depends on the regulation around the MPA. So some marine protected areas are listed as multi-use, which allow fishing and which allow telecom cables to go through them, but it depends on how it's defined at the onset of the kind of the start of that MPA. I have less insight into that, how that process works in Canada, but in the US, there's some marine protected areas that are governed by states. If they're within state waters, which in the US is 3 nautical miles from the coastline. If they're in federal waters, you often need to go through higher levels of approval, not just at the agencies, but also at a congressional level, to change what's allowed or not allowed in the marine protected area. Okay, next question from David. What are the most challenging activities while constructing the offshore wind farm floating? So I'll quote maybe I'll answer quickly for fixed. I think the actual installation of the foundation is the most challenging piece. It's noisy and you have to mitigate for impacts to marine mammals. It's also difficult and you have to mitigate for disruption of sediment and sediment plumes and then potential erosion. There's methods to do all this and they have been implemented, but it is a expensive and I'd say high stress construction environment. For floating, my understanding is most of the challenges are more onshore at the port. That's where you're building everything, and that's where, pre-construction, you have to design the equipment. I think once the design is proven and taken to shore, taken offshore, it's fairly standard practice to install a mooring line. Even in the depths we're talking about, 1,000 meters deep, moorings are installed frequently. So I think it's designing the substructure that's going to function the way they want, and the industry kind of has not narrowed in on what's the ideal design there. So I think that design and fabrication of the substructure is probably the biggest challenge. Then the last question I see, it says, is there a difference between a radial system and a generator tie-in transmission system? Also, are the planned offshore wind projects in the US dependent or reliant on planned transmission corridors within or with Atlantic Canada? So the first question, what I call it a radial system, would be the same as a generator tie-in transmission system. It's just one generator to one point interconnection, and that point interconnection is onshore, connected to the existing system. For the US on the Atlantic coast, there's a lot of development happening there. All of it's planned to deliver power to the US. So there's not a planned tie-in with Canada. I think some of that does come from states on the East Coast have set procurement targets saying by 2035, we need to procure 5 gigawatts of offshore wind power into their electricity generating mix. So when that's the case, they're going to develop transmission solutions or support transmission solutions that feed the power to their state because they've mandated that they want it and that they need it.
Thank you so much, Mark. Thanks for getting through all those questions. And thank you, everybody, for your questions. That was a great introduction, Mark, overview. I think it was super helpful for giving us a common language and a common framework to work with in Canada. So we really, really appreciate your time. We will be following up with all participants, but if any of you have ideas or questions about upcoming webinars, please feel free to get in touch. As I said, we're really hoping to respond to your direct questions and needs with respect to this series. So hope we've started to do that today, and we're open to your feedback going forward. So thanks, everybody, and have a great rest of your day.
Thank you. Bye.
Thanks.